Hi, John Hess from FilmmakerIQ.com. Today we're going to take a deep dive into dynamic range by looking at dots of light and Excel charts. What fun! We'll also get into gamma, log, ISO, shooting raw, and ETTR, while hopefully trying to avoid popping a blood vessel in my poor little brain. Simply put, dynamic range is the range between the lowest of something we can measure and the highest. Let's take this good old-fashioned meter stick. The most it can measure is 1 meter, or 1,000 millimeters. The smallest it can measure is 1 millimeter. Below that, we have no accuracy. So we could say this meter stick has a dynamic range of 1 to 1,000. You would never say that about a meter stick, but we're among friends here, so I won't judge. In photography and motion picture, our job is to capture the light from a scene, and that light comes to us in a range. In my video on exposure, I called this the scene luminance. And if you haven't already watched that video, I would strongly recommend it, as we'll be referencing it a lot in this course. Unless we're shooting a flat white wall, a typical scene is going to have a range of luminances. In other words, parts of the scene are going to have much more light coming in per unit squared, or more concentrated light, than other parts of the scene. In more layman's terms, some stuff is going to be bright and some stuff not so bright. So dynamic range for an image creation tool is the difference between the brightest part of a scene that our tool can measure and the darkest part of the scene. For a digital camera, this really means the maximum signal to noise ratio, but we'll get into that in a bit. Back to our meter stick analogy. From a meter, the most our meter stick can measure, down to the millimeter, the least it can measure before losing accuracy. But in photography, instead of using a defined and set in stone unit like the millimeter to measure our dynamic range, we use an exponential system called f-stops, or just stops. A stop is the doubling or halving of light intensity. So each stop up is twice the brightness as measured in candelas per meter squared than the previous stop. With me so far? Now let's throw a wrench into our basic understanding by first looking at the all-important but confusing and often misunderstood instrument, the human eye. To better understand how dynamic range works and to get a real-world experimental data, I built this dynamic range demonstration set. I took a piece of wood and drilled 15 holes. In each hole I placed a thick piece of acrylic fiber optic and topped it off with a 1-watt daylight blue LED. If you want to learn more about how to build simple circuits, check out our video on how to wire LEDs. The light from the LED will shine through the hole, and the fiber optic will guide the light so it's nice and concentrated on the other side. There I laid down pieces of ND gel, using push pins to hold the gels in place. I have a 0.3 gel, which is 1 stop light reduction, 0.6 gel, which is 2 stops, and 0.9 gel, which is 3 stops. Layering them, I built a system so that each light in the system is 1 stop darker than the one immediately next to it. Using a light meter in spot metering mode, I took as best a raw reading as I could from each light, ranging from about 110,000 candelas per meter squared on the high side down to just 7.5. If I compare my readings from the light meter to what the hypothetical readings ought to be, starting with 110,000 candelas per meter squared and dividing by 2 all the way down, I found that my demo device gives surprisingly accurate results for a homebrew system. It's not perfect, but it follows the hypothetical curve pretty closely. Okay, so here's where things get a little weird. Take a look at this series of lights. The diminishing brightness looks pretty linear, doesn't it? Like the brightness is diminishing in relatively even steps. If we go back to the graph of the light meter readings, we see an exponential curve. Each stop is supposed to be double or half the brightness of the one next to it. And since a camera is nothing more than a fancy light meter, why does this gradient that I captured with my camera look so even? If we put it on a waveform monitor, the steps look pretty linear. Shouldn't it look more like this? To answer that question, we have to go into the world of psychophysics. It's really just a branch of psychology that deals with the relationship between physical stimuli and mental phenomena. We begin in the 19th century with the work of Gustav Fechner, one of the founders of experimental psychology. Through his experiments, he discovered that human perceptions of sight, among other things, is proportional to the logarithm of the actual intensity measured with an accurate non-human instrument like a light meter. What all that means is small changes in intensity, in actual intensity on the low end of the curve, can result in big changes in perception. But as the stimulus gets more and more intense, you need greater changes in intensity to get the same perceptual change. Now think of it like movie popcorn. You know when your friend gets a bucket of popcorn and he lets you have a small handful of it? You start off eating one kernel at a time and the salt and the butter are just heavenly, right? If you buy your own bucket, it never tastes as good. Sort of like Fechner's law. When you have a small portion, small stimuli make a big impact. But with your own bucket of popcorn, after a while, your taste buds get satiated. So to get that same sensation, that same hit of salt and butter, you need to start eating 2 kernels at a time, then 4, and then just shoveling popcorn in your face. The difference there is our taste buds need time to reset. But taste response is also following this Fechner law concept. In 1957, Stanley Smith Stevens updated this with the Stevens power law, defined generally as this. Describe our sensitivity to stimuli from audio to warmth to heaviness, taste, and even electric shock. We just have to change the value of the exponent. For sensitivity to light, Stevens set it to 0.33. So let's take our hypothetical light readings from my light experiment. It's just a little easier and cleaner to use hypothetical values right now. We'll come back to the real world set later in this video. I'll convert these numbers, these hypothetical numbers, into the percentage of the top reading. Then we take the values and plug them into Stevens' power law using 0.33 as our exponent. This yields the following fractional exponent curve. This is how we experience stops of light. Remember, each point on this curve is double the one on the left. Now, if we measure the distance between the stops of light, we yield this curve. And notice how flat this is. Although it's not a flat line, it could easily be construed as linear. This explains why the lights in my dynamic range demo look the way they do. Now, fortunately for early TV manufacturers, the properties of cathode ray tubes in televisions kind of acted in a similar way to our eyes. Let's take a moment and step away from the psychophysics and come back to the real, measurable world. In our universe, light addition behaves linearly. If you have 100 lumens and you add 100 lumens, we have 200 lumens. If instead you started with 1,000 lumens and you added 100 lumens, you'd have 1,100 lumens. It's linear, despite what our brains tell us. A celluloid film has its nuances and eccentricities, but gathered light in much the same way and reflects the psychophysics of our eyes. But electronic camera sensors, now those things see the world as it really is, in a linear fashion. We get into the workings of the photodiode in our sensors video, but for now, just know that if we add more light to our camera sensor, it will produce more photoelectric charge. One more unit of light means one more unit of charge, and it stays in that linear relationship up to the point where the pixel can no longer hold the charge, and we get blooming and clipping. If we graph this, we get a straight line, and I've gone and notated where the stops lie on this graph. So why didn't early TV engineers just take that linear curve from our camera and blast it straight onto a CRT screen? Well, there are a couple reasons. First of all, a TV isn't capable of putting out the kind of light range that reality can. Try watching an old TV outdoors or even a room with a bright window. The device simply didn't put out the dynamic range necessary to compete with reality. But there's something else going on. When engineers measured the light output of a CRT display and compared it to the voltage input, they discovered that, guess what? The relationship between the two was not linear. In fact, it was a power curve, just like Stevens' power curve. Engineers described it as I is related to V to the power of gamma. For CRT televisions, this gamma was in the neighborhood of 2.35 to 2.55. For computers and modern electronics, it's 2.2. So from here on out, let's just use 2.2. If we gradually increase the power of the incoming signal from 0 to 1 volt in a linear fashion using a gamma of 2.2, this is the resulting real light output. Not perceived light, but real light output. But our goal is to have a CRT monitor put out this linear curve to match, or at least closely match, what we would experience from reality. So how do we do that? Well, we have to take the linear light data that's coming from our camera and bend the curve in the opposite direction. Take the inverse of the gamma. So if we take this linear light graph and apply the inverse of our monitor's gamma value, in this case 1 divided by 2.2, or 0.45. This process is called scene reference gamma, or encoding gamma, or optical electro transfer function, OETF. We are converting optical energy into electronic signal. Then when this signal is sent to the CRT monitor and it goes through the CRT's gamma, we're left with this implicit linear light output, just like the way it was captured. Now, modern TVs and LCD displays don't have this response issue, but they still compensate, reprocessing the incoming signal with a gamma of 2.2. This is called display reference gamma, decoding gamma, or the EOTF, electro-optical transfer function. And the resulting curve is back to our linear light values, or as close to it as given some quirks here and there in the engineering process. This curve is called the OOTF, optical to optical transfer function. So if modern displays don't have this response issue, why are we still using gamma? And what does this have to do with dynamic range? Let's compare the linear curve with the OETF curve using standard gamma. I've notched out the stops on each of these curves. Without getting into what IRE and voltage are, let's just talk about it as a digital scale using 8 bits. That's 8 binary bits for a total of 256 possible values from 0 to 255. In the linear curve, notice that the top stop takes up 50% of our range. That means values between 128 and 255 are all dedicated to defining the brightest stop our camera can handle. The next brightest stop takes up 25%, or values between 64 and 127. The next brightest stop is defined by only 12.5%, or values between 32 and 63. The next stop only values between 16 and 31. The next 8 through 15. The next 4 through 7, then 2 to 3, and we're done. That's 8 stops of dynamic range, but if we count those last 2, but man, there's not much information down there. But look at how the information is distributed. That top stop hogs half of our data. If you remember back to our psychophysics discussion, our vision actually is more sensitive in the low intensity than the high intensity. Now let's compare this to the OETF curve with the encoding gamma of 0.45. Immediately, you'll notice that the stops are more evenly distributed among our range. The first stop, instead of occupying 50%, only occupies 25%. The next occupies 20%, the next 14%, then 11%, 7, and then 4. That 7th stop using a gamma curve covers 10 possible values compared to only 1 possible value when working in linear. So this gamma correction not only compresses the light data, but also more resembles the natural response of the human eye as given by Stephen's power law. After all, gamma is just a power function. So we really kind of lucked out there that old CRTs behave the way they do because they naturally compensate for how our vision works, forcing us to put more information down there in the darker parts of the image where we are more sensitive to it. Now, since we're still using 25% of the signal for that top stop, we can get a little more extra dynamic range by applying what's called a knee. As we just said, our eyes are less sensitive to those extremely bright parts anyways. So why not compress some of that data so we can capture a bigger range? If you're familiar with audio compression, it's sort of the same idea. The knee pushes down the response on the high end, giving us about 2 to 3 more stops for a total of 8 to 9 stops. Now we have to be careful with using a neon video because it can create some weird color shifts in the highlight range. This gamma encoding, now defined for HD at least by something you've probably heard of already, ITU-R recommendation BT.709, or simply Rec 709, first passed in 1990. Now these conventions are absolutely crucial to our technological world because it means the TV that you buy today will be compatible with the television broadcast next year or even 10 years from now, as well as ensuring you don't need to teach grandpa how to use a brand new TV set every time a brand new model comes out. But camera sensor technology keeps getting better and better every single year. Although we have to follow broadcast conventions when we deliver the final video, there's nothing saying we have to capture footage using those conventions. We can use some other kind of formula to bend these curves to get even more dynamic range. The first strategies employed in video cameras were cine gamma and hyper gamma. Now these are differently shaped scene reference gamma curves that responded in various ways that could be used to simulate the response of film or help capture the dynamic range in challenging shooting conditions. This could open up a 7 to 8 stop dynamic range that Rec 709 has to say 11 to 11.5 stops. And then came the technique that probably everyone watching is just waiting for me to talk about. Log. Log is of course short for logarithm, which you remember from math class is the number that a base must be raised to equal that number. So for example, the log with a base of 2 of 256 is 8, because 2 raised to the 8th power is 256. Logs are really useful for working with exponential spaces of magnitude. That's why we use log scales for things like seismic readings, sound pressure, and light. Talking about stops is using a logarithmic scale with a base of 2. So it makes total sense to encode our video signal into some sort of log system. Now I won't go through the math, but here's a formulation that Einar Gamasov of RenderStory came up with to match the kind of log curves out there. Back in Excel, here's a linear light curve with a notch on each stop of light. Here's the gamma curve with the encoding gamma of 0.45 applied. Now here's that linear curve with the following log function applied. That's not a real log formula, that's just one I came up with that shows some interesting properties. With all these curves on the same graph, the first thing you should notice is that at 100% light intensity, or 1, our log curve is only returning 0.6 signal. That means this log system can store even more data than being returned by 100% light intensity. Let's extend the x-axis and add a few more stops of light. We have to go to 3,200% of light intensity. That's 5 additional stops to get the log formula to return an output signal of 1. So that means we can record about 14 stops inside the same signal using this log formulation. Now here's another interesting property of log. Let's look at the differences between the stops. When using log, unlike linear or gamma corrected, these stops are much more evenly distributed. Now since log is not a viewing standard like Rec 709, every manufacturer has their own formulation that they think works best with their own cameras and sensors. C-log, D-log, J-log, N-log, S-log, V-log, log-C, red log. All of these are manufacturer-specific variations of a log curve designed to best utilize the sensor from that particular brand of camera. But they all have one thing in common. They don't look right when viewed on a TV. So when you record log, you have to apply some sort of correction in post to turn that log curve back into an acceptable traditional gamma curve to make it appear correct on a Rec 709 screen. The difference is you could potentially have a lot more information to work with in terms of dynamic range. Let's talk ISO. ISO is one of those topics that seem to enrage certain sectors of the online photography blogosphere, and I suppose there is some justification. For the longest time, people have been equating ISO, or camera gain, on digital cameras that is, with film speed. And for a while, that analog made sense. But advancements have made ISO or gain somewhat of a different beast. In my video on exposure, I pulled ISO out of the exposure triangle, flattening that stupid triangle into a straight line, which I called the pathway of light. Exposure in that case is only aperture and shutter speed. You're controlling the brightness of the final image. The last step is the ISO, or camera gain, which in the most simplistic description is the light sensitivity of the entire imaging system. There are sectors that will roast me alive for saying sensitivity and ISO in the same sentence. Okay, ISO is not quantum sensitivity of just the sensor. The sensitivity of the sensor never ever changes. It is set at the manufacturing stage. Remember, 1 unit of light equals 1 unit of photoelectric charge. The ISO of a camera refers to the sensitivity of the entire system. So when a camera says it's shooting at ISO 100, then we would expect a certain average scene luminance to give us 18% middle gray. And if we shoot at ISO 200, we would expect half of that luminance to give us the same middle gray. The camera system at ISO 200 is twice as sensitive to light as ISO 100. But what's really happening inside the camera is we are introducing more amplification, or gain, as we step up the ISO. This gain is similar to the gain knob of an audio mixer. In fact, it uses the same decibel system. Now, here is where we need to introduce the concept of signal noise. When we first started, we said that dynamic range is really the signal to noise ratio. So let's draw a noise floor and a max signal ceiling. Now the dynamic range is the range from where the signal and the noise floor meet to where the signal meets the maximum allowed signal. As we gain up or go up in ISO, we're essentially changing what scene luminance will return middle gray. If we go up one stop, what was middle gray will move up one stop to being one stop overexposed, and what was one stop underexposed will now be moving up to middle gray. The traditional way of thinking about this was, as we gain up or pull up this linear exposure graph, our noise floor comes up with it. So if we go up one stop, our maximum signal stays the same, but we lose one stop of dynamic range because the noise floor is one stop higher. And in certain ISO ranges and on certain cameras, this is indeed what happens. The higher the ISO, the smaller the dynamic range. However, noise has many authors. Noise could come from weird quantum fluctuations or sensor read noise, in which case those may get amplified as you raise the gain ISO. But more often than not, the noise comes from the analog to digital converter or some other electronics in the camera body that has nothing to do with the exposure, in which case it may not be amplified along with the gain. And with cameras now being developed with noise cancellation at various points in the signal path, it's even more confusing. Now yes, at some point, as you increase the gain or ISO, you will decrease the dynamic range. Where that's at depends on the camera, so test, test, test. But there is one other really interesting and counterintuitive point that I want to cover in regards to ISO and dynamic range. In fact, it's the reason why I wanted to do this video. Let's say we have this graph that represents the response of a camera at a certain ISO setting. Let's also say that at the top upper right-hand corner, when the signal meets the max signal, is where our sensor completely becomes saturated. There's no more possible photoelectric return on this sensor. Now, let's reduce the ISO by one stop, but do so in a way where we shift the signal and the noise floor down together. Now, what was middle gray originally has moved down one stop to being one stop underexposed. Our noise floor is one stop lower, but look at that max signal. Since our previous white point was at the saturation limit of the sensor, going down one stop ISO just means our white point is one stop lower than the maximum allowed signal. Our dynamic range is still the same because our noise floor is one stop lower, but we are putting more stops below middle gray than above it. I can demonstrate this with my real-world demonstration set. Shooting at ISO 800, which is the native or base ISO for shooting with C-Log2 on my Canon C200, you'll see I have about 6 stops above middle gray and about 9 stops below. But as I go down the ISO scale, the entire waveform is squeezed lower down to about ISO 200, the lowest natural ISO setting. I now have only 4 stops above middle gray and 11 stops below. And if I go down to the extended ISO 100, I have 3 stops above middle gray and now only 10 stops below. So in extending down, I've actually went from 15 stops down to 13 or so. The Arri Alexa also demonstrates this kind of behavior. The difference being that when you go up to ISO 1600, it actually puts more of the stops above middle gray. I found similar charts for red. I'm sure other cameras also behave this way when shooting in some flavor of log. So what does this all mean to the cinematographer? If you are in a very bright situation, say outdoors shooting a scene with big fluffy clouds and you want to protect the gradations of those clouds, stop down your exposure, that's aperture and shutter speed, and shoot a higher ISO. If you have a lot of shadows, say you're shooting a moody interior scene with your characters' faces in shadow, and you want to protect those details, consider upping your exposure, adding some light, and shoot at a lower ISO. I know this is counter to basically everything you may have learned so far. You think dark situations should be shot with a higher ISO, but that's because we've been conditioned with this exposure triangle and why we need to stop treating ISO as part of exposure. With modern techniques, ISO should be considered a different final step in the image creation process. Let's talk RAW. RAW is quite simple. It's just the data that comes off your sensor. Pure, simple numbers in a table with some metadata. In its essence, RAW is not an image, but the raw ingredients to make an image. You need to take those ingredients, decode it, debayer it, pick a color temperature, apply color space, along with gamma and log encoding, and in some cases even pick your gain/ISO settings before you can actually see the image file. Now, why would we take the time to do all of this? Well, by bypassing all that image processing, we get a file that takes everything that the sensor actually sees. And instead of relying on the small onboard image processor to make decisions there and then while we are shooting, we can save those decisions for post, where we can use much more powerful computers and a human artist at the controls. The downside is file size. RAW is much, much bigger than compressed video. And the fact that we have to process everything means more time in post. Okay, so what does that mean for dynamic range? Well, raw data natively has no OETF curve, be it gamma or log applied to it, although we do apply it in a raw viewer. Raw in itself is straight up linear data. So it's all the dynamic range our camera can muster. So again, let's look at this linear curve. I'm getting tired of saying this. Notice how half of the data in the raw file is used to store the top stop, the brightest part of our image. Now, we could expose as we normally would and record our data down here, put our middle gray smack dab in the middle of our 15 stop dynamic range with 7.5 stops above and 7.5 stops below. That will give us plenty of room to roll off the highlights and we would still get all the control of shooting raw. But the thing is, most scenes don't need all 15 stops of dynamic range to cover everything that we care about. Most of the time, you really only need 6 to 8 stops. So why not overexpose our image? Move our middle gray from 7.5 stops below clipping to just 4.5 stops. By moving our exposure up 3 stops, we give middle gray 8 times more data to work with. And the same goes for every stop below middle gray. And with 8 stops seen, our whites are still not yet clipped. Then in post, we pull down the exposure 3 stops. That buries the noise and we get a cleaner and more richly detailed image. This is called exposing to the right, or ETTR. And the right is a reference to the histogram that photographers use. We are putting data on the right side of the histogram. To demonstrate, here's a shot from my Canon C200 recording at what the camera thinks is a proper exposure. I'm recording in the Canon RAW light, and we are taking the raw data and applying a Rec. 709 gamma curve to it. The image looks nice. Then I push the exposure up 3 stops using a combination of removing ND filters and a slower shutter speed. We are letting 3 stops more light hit the sensor. That's 8 times more light. Still using that Rec. 709 gamma curve, we see the image is now completely blown out and unusable. That's to be expected because Rec. 709 was not made to handle all this highlight detail. Instead, let's take the same raw data and apply a Canon C-Log2 gamma curve. C-Log2 is Canon's widest dynamic range log format. Now we pull the image down 3 stops and then grade it. The result looks pretty much the same, but if we zoom in, we can see the ETTR image has a lot more detail in the color and less noise in the shadow. That's because we're making better use of the data range when shooting RAW. The original footage was fine, but the exposed to the right footage is noticeably cleaner. Now you have to be careful with ETTR in that you don't want to accidentally clip highlight details that you want to preserve. Now many cameras and video recorders are starting to come with HDR previews, so you can actually visually guess the graded exposure rather than just going on blind faith. And HDR is another topic altogether, and the next real step in camera evolution now that we're kind of exhausted with resolution at 4K. But I digress. Now you must use the exposure side to get the benefits of ETTR. You must add more light through removing ND filters, opening the aperture, or extending the shutter speed. If you expose the right using only your gain and ISO, you are also raising the noise floor, so when you grade the footage, you'll find you really won't get any benefits in terms of noise. The magic of ETTR is capturing more light, and you don't get that with increasing the ISO because you're not actually increasing the light. If you have a scene that requires a lot of dynamic range to render, say in an interior shot looking out a window that you don't want to blow out, then ETTR may not be really viable. You can use the idea of ETTR with log, gamma, and even Rec. 709, but those spaces are really more meant to be shot at the proper exposure. Furthermore, because these stops are much closer together, you could run into banding issues as you try to separate and recover information from your highlight. A lot of this is dependent on your recording bit depth, and as always, test, test, test. Okay, this has been one of the most difficult topics I've yet to cover in one of these videos, at least for me. I stared at the charts and graphs over and over again, trying to make sense of dynamic range, separating out psychophysics from reality. I hope I've given you some basic ground level understanding of how dynamic range actually works. There's a lot more engineering that I don't have time to cover and frankly is well above my head. But I hope to give you a layman's understanding so when you hear a camera manufacturer talk about dynamic range, you'll get why it's important and more so, how to use it effectively. If you like this video, then STTR, scroll to the right and click like and subscribe and ring that bell. You can also support what we do by joining our Patreon, as every little bit helps. Check out our merch store for cool filmmaking apparel exclusively from Filmmaker IQ. If you didn't like this video, well, feel free to buy 100 shirts, which you can burn in a ceremonial effigy while casting a hex on my stupid, ugly face. Until next time, my friends, go out there, make the most of your dynamic range, and make something great. I'm John Hess, and I will see you at filmmakeriq.com.